I live in the capital city, which is Berlin. It's quite interesting, I think, and it's happening very close to my home right now, which is the Anga, and it's very interesting to see the city with capital, and meet new people here, uh, and so it's just pretty much interesting experience to hold an copy 30 in my city. Luca, do you want to talk about you?
Yeah, hello everyone. My name is Luca, and Carlo is my research partner. We're from the Feynman Group, Grupo Feynman, here in Brazil. And our research group talked about uh, quantum computing and programming marathons we do here in Brazil and ICPC doing the world. So I'm pretty happy to talk with everyone about quantum computing because it's a field that's it's too so interesting. We have too many applications like quantum cryptography, quantum errors, and every application we see it's gaining more and more new papers and new perspectives in the science. So it's a field that's growing too much in nowadays, and we're very happy to talk with everyone here. First, I like to say we live in Brazil, so our main language is Portuguese. So if something we said don't make sense, you're if someone don't understand something we said, you're free to ask everything, and we can repeat for everyone. So I'm not here to talk too much. I'm here more to do a support action with Carlos. Me and he made a slide, and we will presentation our teams for you.
Yes, continuing my talk, I think, as Lucas said before, quantum computing is the most interesting field. I mean, I've been 1 year along working with it. I think 1 year and 4 months, 1 year and five
Two
months,
years,
maybe.
2 years.
Yes, 2 years almost. And it was interesting when I first saw the quantum computing, uh, because it just can make together all the things that I wanted to learn, which is physics. I wanted to learn mathematics behind. I just wanted to keep in the front line of a researching field that can change the world and everything that we know right now, just like AI. But quantum computing holds a promise much, much longer because it can change it drastically how we face the world together, the research, the things that we can do. And it's strongly, I believe, that this technology will change the century. I think, well, most people think it's AI. I really believe that AI is changing this decade, but I think quantum computing holds a large promise. It can change this field, can change the century, and it can change the world we live and we know us together. And we just have much more interesting fields, of course. We just have optimizations, we just have quantum machine learnings, we just have quantum chemistry, just have cryptography that quantum computers holds the promise to break the whole world of cryptography. And this would change the world forever. It's just a one way road, and that's all I have to say. Do Can we begin, Oscar? Oscar.
Yeah, guys, I'm sorry. My internet connection it's not so good. Can you repeat what you said?
Oh no, I think can we start? How can we do? How can we proceed?
Uh, I think that you have a presentation, right?
Yes, we do have a.
And all right, so you can even share your screen and begin.
Oh, of course, can I just show my presentation that me and my partner we just developed?
All right, John, you're free to go.
All right, just a minute for sure. Uh, Can you see my screen right now? I'm gonna start my presentation.
Yeah, we'll see it.
All right, can we start?
Yeah, you can start, please.
Well, first of all, again, my name is Carlos Henrique Miranda Esteves. I'm an undergraduate researcher at FAPESPA, and I'm also a computer engineer from CESUPA. And today I'm going to talk about quantum chemistry and quantum error correction code with my partner, Luca Nobri, Utrandala Banerjee. And we just started this talking about quantum chemistry and what we can do with the quantum chemistry. And I just going to talk about what is the field, what do we have, what is our main perspective, and what quantum computer can just become quantum chemistry better, can make it better. And I'm just going to start this lecture talking about the Schrödinger equation. So this is quite interesting because the Schrödinger equations describe many quantum aspects. And we use it also to describe as molecules. We use to describe atoms by itself and many other quantum behaviors that we have. First, we just have functions that is here, the wave functions that we are trying to discover. And we just have the spatial part, and you just have the time. And this is interesting to notice that isn't a normal functions, it's a differential equations. And that these equations, you just needed to find the problems that you wanted to solve. So there is many cases. There is the unidimensional case, which is the simple case that we treat before we enter in the three-dimensional case. And when we try to understand how molecules, how atoms behave, we just use the Schrödinger equations in the three-dimensional or spatial. And this isn't an easy task, right? Solving the Schrödinger equation is not easy to solve because it involves many kind of operators. When we talk about molecules or atoms, we just have the kinetical operators, we just have the repulsion between electrons operators, we just have the nucleus operators, kinetical operators, and so on. So we just have too much operators to solve it. It became much difficult to solve in the paper or to try to solve by hand. So we rely on simplification methods. The first methods that we have here is the Born-Oppenheimer approximations. And yes, it was developed by Max Born and Robert Julius Oppenheimer, the father of the atomic bomb. And this is just a brilliant contribution to the fields of quantum chemistry. And this approximation, how does it works and how does it become much more easy to solve. Right. Remember when I said that the operators that we work with quantum chemistry relies with kinetical operators. We just have the kinetical operators of nucleus. We just have the kinetical operators of electrons. We just have the operators, we just have the attractions between electrons and nucleus. We just have the repulsion between electrons. So all these operators, all this energy that we have in our systems, if it is an atom or if it's a molecule, we just need to count it. We just need to understand it and take it in considerations when we just put it all in the Schrödinger equation. What the Born-Oppenheimer approximation does is just simplify it all. It just assumes that the electron's movement is just too much faster than the electron, than the nucleus motion. So we just have the electron, which is much faster than the nucleus, and we just can assume that the electrons are moving around fixed nuclei. So we just state that the nucleus is stopped and that the electron is moving around the nucleus. So these simplifications just take out many other operators. We cannot simply we just use no longer the kinetical operators of nucleus and the many other operators. We just use the electronic or the electron operators. Now we just have the fixed nucleus, which becomes a constant energy because we just fix the positions on the three-dimensional coordinates. And these three-dimensional coordinates that we have now is just becomes constant. So it became constant in all energy and function deductions that we are trying to solve. And we just focus on the electronic problem, which is solve the Schrodinger equations, not for the whole system, but just for the electrons, just for the electronic problems. That is what we have here. And we just have the kinetical operators, we just have the repulsion between electron operators, and so on. So as you can see here, the original wave functions that we are trying to discover is simply the electron wave functions, which we simplified to solve using the Schrodinger equation, simplified by Born-Oppenheim approximation, and the nucleus part, or the nucleus wave function. And as we can see here, we just have coordinate dependencies, which means that for different nucleus coordinates that we just have different electrons wave functions. And that's how we work. That's how we have the Born-Oppenheim approximation. This is the first step before we just get into the ab initio methods. And okay, this is great. We just have approximations. We just have a simplification of the methods. But everything, it is still difficult. It is still difficult to try to solve the Schrodinger equations because, again, it is differential equations and we just have too much operators. The most difficult task here is not the differential equation by itself, but is the electron-electron repulsion operators. This is difficult when we try to solve any kind of problems in the molecules, in the atoms. The most easiest case is just the hydrogen molecule, which is the simplest case we can treat. We can just understand how it works because it's simple to solve numerically or just to solve it mathematically. And we rely upon the ab initio methods or the quantum chemistry classical methods that we have, which is our next step. We just have the ab initio methods. The ab initio methods is just more than the simplifications that we have before. Because now we just don't have the Schrodinger equation by itself. We just still have an equations, which is here a differential. I mean, integral differential equations, which is a little bit more complex. But it is simplifications from the process that we have since the beginning. And why do we need this? Because now we do not treat the interaction electrons directly, because it is the problem that we have since the beginning. It is what becomes the Born-Oppenheim is still difficult to solve. And here we just treat this interaction electron not directly, but rather than a field. So instead of treating this interaction of this electron with this, and the whole system, we just treat it isolated, interacting with a field that others electron creates for it. And this became much more simpler because we can make our solution numerically. We can solve it numerically, and we just can treat the whole process as matrix equations. Um, I am not gonna to enter in these details of what it is or how to solve or what is the consequence. But I'm gonna focus in the other aspects of it. Uh, this here is the first ab initio methods that I'm going to present for you, which is the Hartree-Fock methods. It's the simplest case that you can even imagine, because when we have nowadays the classical quantum chemistry methods, we just use the post-Hartree-Fock methods. Why is it called this? Why the other methods are called the post-Hartree-Fock methods? Because this is the most simplifications that we have from everything. The methods that comes after the Hartree-Fock just to try to correct the energy correlations and electrons correlations that Hartree-Fock ignores here. And they just add more restrictions, add more iterations, more complexity to the problems, and the energy and the wave functions we are trying to solve became much more solvable, became much more precise. Of course, this isn't simple. It all came with a cost, which means the more complexity we add to a system, the more precision we add to our solutions, requires much more computational resources such as memory, processing, and time. And this is the Hartree-Fock methods. Right here, we just have an approximations of the ground state of the wave functions, which is we just have the wave function here that is found by the previous Hartree-Fock methods. And I wanted to say that this is spin orbital equations, which is the spatial wave functions of one single electron together with a spin, which means the spin could be up or the spin could be down. This is our approach. This is our approximations that we have for the exactly wave function. Of course, we just sacrifice precision over the solvable method. So we just have here our approximations to the wave functions, the ground state wave functions. And this is the energy. And I just want to understand that everything is all right. Can you understand what I said? Oscar,
Yes.
everything is all right? There are some more
Yeah.
questions or not?
I don't know if the participants have questions, but it's quite good. It's all right. It's all good. You can
All
continue.
good. All right. So we just move on to the next part of this lecture, which is quantum computing. And I just wanted to say this interesting Feynman quote, which is nature isn't classical. If you want to make a simulation of nature, you'd better make it quantum mechanical. And this is quite interesting because Feynman said in 1981, and this paper just was published in 1982. And the most interesting part of it all is that quantum computing was a boring field. It's still in the beginning. Of course, Feynman didn't invent this field of quantum computing. But he became one of the most popular voices in that time of propagating the idea that quantum computers are using quantum mechanical properties to compute the properties of all the systems. Just was he became all popular. And remember when I said the ab initio methods? It's just we need some sacrifices. Of course, we just have all this code to solve the quantum chemistry. We just have to try to understand what is the basic properties of molecules, try to understand the ground state energy, try to understand the excited energies. We just wanted to understand how the system, the quantum system, work out together. But of course, we cannot solve it directly. We just rely on methods, numerical methods, and computational methods, which is the ab initio methods. We sacrifice precision over something that is faster or something that is solvable. And the interesting ab initio methods that I didn't mention here is the configuration interaction. The configuration interaction sometimes can become as a much more complex problem. Became as I think it's a combinatorial problem. I don't know much more, but it is became difficult to solve on classical computers. So of course it can become as a much more precisely, almost perfect solutions, but sometimes we just don't have computers to do it. To try to simulate complex molecules, such as, I don't know, something that can be turned into drugs that can save people or can cure diseases, or simulate even small properties such as lithium batteries, becomes much more complex to do in classical computations without sacrificing precision or sacrificing all the things that we want to know of the molecule. So quantum computers hold this promise to, together with quantum chemistry, uses the properties of qubits. And using the properties of qubits, we can simply expand the wave functions and use a quantum computer to calculate the expectation value and understand what is the ground state, which is the next idea I want to show to you, quantum chemistry with quantum computers. And right here, we just have a simple image, which is calculate energy estimations. And what I'm trying to say here, what I'm trying to show here, is the idea of a variational quantum eigensolver. Variational quantum eigensolver was first proposed by Peruzzo and many others researchers in California for IBM and others research institute. The main idea is try to use quantum chemistry problems and try to use quantum computers to simulate the original wave functions, or at least the space necessary for the wave function. And since quantum computers can expand much more the space using superposition properties, he thought, well, what if we can just use quantum computing to expand the original wave functions, which much more spaces that quantum computers allow us to do, and use it to calculate the expectation values, the ground state energy, or even the ground wave function. And the most interesting approach here is that it's not 100% classical, neither 100% quantum. We just need a hybrid approach here, which means these algorithms run partially on a quantum computer and partially on a classical computer. And why this is an interesting approach? Because the quantum computer does all the hard work that is impossible to do on non-classical computer. It's just simulate the wave functions, collapse, calculate the expectational value, and generate an estimate for the ground state energy. Of course, we introduce here parameterized wave functions, which means just have one wave functions, or a guess for all wave functions, which we call ansatz, and it has many other parameters here. And with these parameters, we just complete the expectational value, and we send it to a classical computer. The classical computer, we use now an optimization algorithms, which is he just try to run it. He just use the optimization algorithms and send the new parameters to the quantum computers. And we just keep going on until the classical optimization process no longer works or no longer can find an optimal or even find the most approximate solution. Of course, again, this is an approximations. Quantum computers can hold this promise because since we can use the qubits properties of superpositions, we can just use much more space for our simulation using less resources. And this is a variational quantum eigensolver works. Of course, the scientific community didn't stop it here. We just now do not use this term variational quantum eigensolver. We just have a term that is much more complex, which is variational quantum algorithms. And why I'm saying this? Because right now, the variational quantum eigensolver, variational quantum algorithms, is used for quantum machine learning, quantum optimization problems, quantum algorithms, and so on. So we just have a large and many others quantum problems that can be solved with the variational quantum algorithms. Do you have some question, Oscar?
No. At least me, I don't have any questions.
May
And
I proceed?
yeah, you can proceed, please.
All right. So all I've talked is just a perfect situations. I mean, we just have a perfect computer. We just have everything is going on. We just can simulate systems. And if we increase the number of qubits, well, we'd rather be, we just ended up with a better systems. Of course, this is perfect, but the reality is that quantum computers isn't perfect today. We just have problems in trying to simulate molecules. We just have problems in trying to simulate these properties because quantum computers nowadays solve from the noise problem. And this is a major difficulty today to reach the fault tolerance quantum computations. I mean, trying to solve any algorithms with noise or try to understand how the result works with noise is just a challenge today in the fields of quantum computations. So we have a much more ability. We have the ability to simulate much more complex molecules, to simulate atoms. We just have to solve this problem, which is an engineering problem. And of course, when we just have the quantum computing, we just have this hardware engineering problem. There are many other problems that we need to solve before they will become fault tolerant. Of course, for quantum chemistry, we don't use quantum error correction codes, which is the next part of this lecture. We just use something that is error mitigation process. The error mitigation process is much more cheap than a quantum error correction code, and uses the classical algorithms again to try to estimate how the quantum computers would work without noise. So we just calculate it multiple times with a little bit of noise, and again with 2 times of the original noise, 3 times, and so on until we have so much noise, and then we calculate how the whole system is without noise. Again, we just do it with a simple optimization process. We just use it with the variational algorithms instead of pursuing a quantum error correction code. And our next topic here, we're just going to talk about quantum error correction codes. This is an interesting field. I've been working recently with the quantum error correction, and many things are happening in this field. So there are many papers, there are many lectures available on YouTube, on even on Coursera, and there are many frameworks available to work with quantum error correction codes. Personally, I've used Qiskit. Many years I've been using Qiskit. It was my first SDK, my software development kit. Next, I just move on to Penguin to just use the high level instead of the low level and bare metal. So just use the Penguin to work with quantum chemistry, to work with quantum machine learning, and so other processes that need a high level programming, high level quantum computing. So yes, just me using Qiskit and Penguin. And most recently, I've been learning Circ and the Steam library. Circ, it is very interesting to work with because it has the Steam library. The Steam library is just the Google library, such as Circ, and has this whole development kit that allow us to implement the error correction codes that allow us to simulate how our surface code want to work and how we're going to extract valuable information about what is going on circuit without trying to figure out by mechanical process or hand process. And I just wanted to start this new part of this lecture about classical information and quantum information. Well, classical informations just is simple. We just have two states available. We just have a 0 or we just have 1. Quantum information is something more complex. We just don't have these states separately, but rather than we can use in a superposition. Of course, we can have isolated just the cat 0, which is classical analogous to a 0, and you just have cat 1, which is on quantum analogous to the 1. And together they can be in superposition. And nowadays we just have errors that can happen in our quantum computers. So for example, the process of superconducting qubits can suffer from something that is going from outside of our fridge or quantum computers. It can lose process to heat, noise, or even cosmic rays that can affect the computations and drastically change the information that we have been storing. So when we just try to understand error corrections and error correction codes by itself, we just need to understand what is the classical informations. Because if it's worked for classical informations, can we extend it all to quantum informations? And the answer is simple and short. The answer is no. We cannot simply extend all the concepts because, again, if we measure a qubit, well, we simply lost the information that has been stored in that qubit. And we cannot, of course, duplicate the informations. We cannot simply take the informations and duplicate it with all the qubits because we are limited by the no-cloning theorem, which is a theorem that simply limited the computations and simply says that we cannot clone a state, a quantum state by itself. And with all these limitations, of course, we can simply try to understand what error correction is or how it works. And first, I just want to introduce you the error models that we have. First, here we just have our matrix available. We just have the identity matrix, we just have the X matrix, the Y matrix, and the Z matrix. Together they forms the polygroup, or simply the poly matrix. And if you understand the classical quantum mechanics, you have been familiar with all these matrix. But of course, just let me introduce it. First of all, these matrices just realize simple operations that we can perform on qubits. And here we just have an error model. I mean, each time we just perform a computation, we just have a probability of it being on the original state that we have, that we wanted it to be, we just have a probability of it being bit flipped. So of course we can simply bit flip here. Cat 0 can become cat 1, and the alpha and beta can change places. Of course, that's not what we wanted to do. And of course, we can have a Z error, which is we can have here a phase flip or a phase problem that we can introduce in our quantum state. And of course, we can have both at the same time. We just can have the Y error, which can be simplified by the ZX error at the same time. So when you just have the error model for our quantum computation, is something that like this. Of course, in classical information, it's much more simple. We just have 0 and 1, just a bit flip. We just have 0 becoming 1 and 1 became 0. But of course, when we come into across the quantum computation, we just have these problems that may occur during our computational phase. We just have the state being left by alone by itself. We just have a bit flip error that can occur during computation. We just have this Z error or phase flip error that can occur as a computation. We just have the bit flip and Z flip appearing at the same time. And another interesting thing that I wish to introduce you before I just talk about the surface code, which is the holy grail of the quantum computers that we have to correct errors nowadays, is the stabilizer concept. What is stabilizers? This is interesting because a stabilizer is simply a matrix. Can be a polymatrix, if you just need to be in the simple case, which is just one qubit, or can be a combination of a polymatrix acting in many qubits at the same time. And the property of stabilizers is that if it's multiplied by the original state, it simply does nothing. So right here, we just have the Z acting on cat 0. And if it acts on cat 0, it's simply the state is like the original one, so nothing happens to the original state. And you have the X matrix acting on cat plus state. If it acts on it, well, nothing happens again. It becomes just like the original state. So stabilizers are necessary because when you just put on this operation with our qubits or state of information that we want to assure that nothing or none of this error may occur, we just want it to be something like the original one. So stabilizers just have this behavior if none of these errors occur during the process of our computation. Of course, it isn't perfect, and that's why we need the stabilizers. When we just have an error occurring to our qubit or stored information qubit, the stabilizer is gonna accuse something like the minus sign. So if a minus sign occur in the original informations, it's gonna be stabilized by the ancilla qubits. So you're not gonna measure the original information. The information is gonna simply stay there. And what's gonna be stabilized for us to correct in classical information codes is that the signal that an error occur. Of course, error correction codes can detect bit flip, can detect Z flip errors, and if an Y error occurs, simply the combinations of both X and Y errors. And moving on into the next topic of this lecture is just the surface code. Well, I didn't talk about the others code that we have, such as the 212 code, the 313 code, the short code, the Beaconstein code. I just wanted to show here what we have for most recent, which is the surface code, right? The surface code was proposed by, I think it was Alexei Kiraev, was being proposed. And I have this interesting article, which is Austin Fowler articles paper that I've been reading. And it's interesting because just show how this whole area has been working. And right here, I just have a picture of a surface code, right? So as you can see here, every circle here represents a qubit, right? So just have 1, 2, 3, 5, 6, 7, 8 qubits in a row, in a column, and just have 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12 qubits. So this can be visualized as a matrix or something like a plane, a surface. Each open circle here represents a qubit data. So when you just look at the surface code, it all implementing one logical qubit. Of course, we can use a shorter surface code to create all logical qubits. But of course, they're gonna increase the distance, decrease the distance. And if we decrease the distance, we can simply lose the informations if an error occur. So the distance or the number of qubits necessary to be bit flipped or z flipped is necessary before some error occur that we can detect, correct, and just give back to the original state that it was. So we just have here our logical qubit that is here. So each open circle represents logical qubits, the logical qubits we are trying to create. And the closed circuits or the black circles we have here is just the stabilizers. So for example, if an X error occurs here or here, we can be detected by this one here, which is the data qubit, the measurement qubit. Sorry. If a Z occurs here, if a Z occurs here, it can be detected by this one and this one right here. So this represents the surface code. How we can increase the number of logical qubits? This is quite interesting and is a complex things that we do. It's just we make cuts in the surface, just like a cloth. You can think of it as a cloth or some kind of anything else like a curtain. And if you make a hole here, we're gonna create a logical qubit in this surface. And if you can make any other hole here, we can create any logical qubit, and we can increase this. Of course, I talk about creating logical qubits. You might think, all right, well, we just create logical qubits. What can we do with logical qubits? And this is an interesting question because we need to perform operations in this surface code. We need to perform operations in the logical qubits that we created. So we just use many other tricks that are available to try to reproduce the behavior of the C naught, the Hadamard gate, the X, and the Z operators. Together with all of these operations, the Z operations, the X operations, the C naught, the Hadamard, the S operators, and the T operators, gonna becomes the logical operators. So we just can make all of the work, can make these operators logicals and operators are logical qubits. Of course, this is a complex process, and this requires much and much larger qubits arrays, really qubits, that the quantum processes nowadays can have. And increase the number of qubits does not necessarily means that you just have perfect qubits or just gonna solve everything with quantum error correction codes. There are many metrics here that have been discussed, and that's it. These are being presentations about quantum chemistry and the quantum error correction code. Please feel free to have any questions of the process, and we can start our conversation. Oscar?
Yeah, Carlos.
So I finished the presentation.
All right. I see. So thank you both, Carlos and Luca. Thank you for all of you and the participants and to participate in the session. Um, the talk was truly fascinating, and we all learned a great deal from your insights and perspectives. So, just to finish, we are leaving you in the chat our WhatsApp community link. So, uh,
Sorry, Oscar, can you repeat, please? Oh,
I'm
thank you.
sorry.
The community.
So, we are just leaving you our WhatsApp community link in the chat. So we will keep you updated about upcoming talks, quantum and AI projects, and much more. So, guys, I don't have any more questions and words. So, again, thank you so much for joining us. in this talk.
Well, many thanks, Oscar. Of course, this was a pleasure to be with you. And if many questions arise during the weekend, well, just feel free. Uh, well, I appreciate the attentions.
I think Juan David Costa has a question. Juan David,
Well, of
please.
course, you can do. Oh, of course, there are many books in the topic. May I share some link here, Oscar?
Yeah, you can share your link.
Of course. I have some books here. Is there any specific books that you want, David? There is air correction, quantum chemistry, or anything else I may show here. David? Oh, quantum chemistry would be great. Talking about quantum chemistry, there's a specific book. I just have it right here on my hands, which is used a lot with my undergraduate studies. This name is Modern Quantum Chemistry by Atlas Labo. I don't know if you can see it, but here's the book. I think I can send you right here the link, the Amazon link, which is the Modern Quantum Chemistry. This was an interesting book. I read it on my undergraduate studies for my research and was very interesting to understand it all off the field. Of course, I think it is a difficult book to understand. So if you doesn't have a strong background in quantum mechanics, I strongly suggest you, of course, to build it to understand quantum chemistry. And my favorite book is, of course, the Griffith book, Griffith's Quantum Mechanics. I can send it here too, which is the Introduction to Quantum Mechanics. It's an amazing book too. I use it a lot during my undergraduate research. I think it's working. Yes, it is working. Introduction to Quantum Computer. And there was another book, which is, let me see, I think it's Quantum Chemistry for the Curious. For the Curious. No, I think this book is not. I think it is Quantum Chemistry. Let me see if I have this book here. Molecular Quantum Mechanics is an interesting book too. I'm gonna send it this book right here. This is the Quantum Chemistry for the Curious. And I just have this one book here. So these are interesting books. I strongly suggest you to have a background on quantum mechanics before you get into the next step, which is quantum chemistry, because many of these concepts just going to be necessary for understanding, such as strong linear algebra, strong calculus 3, which is linear equations, and the differential equations. And this book is quite interesting. So if you want to start by quantum chemistry, I strongly suggest to start by this book. Of course, it was from 1992, I think, this book. But it has a lot of concepts that's still used in the field and nowadays. So many of these concepts that you just wanted to study and you just wanted to start it, this book is amazing. It's just a prereq before you just get into the quantum chemistry of quantum computers. So that is for classical computation, quantum computation, I strongly suggest the Introduction to Classical Quantum Computing for Thomas Wong, if you wanted to. This book is also amazing. Do I answer your question, David? Well, thank you. I appreciate your question.
So, there is anyone with a question? More questions? No doubts. Well, I think that nobody has questions. So, Carlos, Luca, again, thank you so much for joining us. And yeah, that's all. Thank you. All right. And thank you to the participants to join us as well.
Many thanks. And as we say here in Brazil, obrigado. So, many thanks for
Thank you.
everything.
Muchas
That was a great
gracias.
opportunity. Equally. That was an amazing opportunity here, and it was fantastic to be with you guys. And I hope you may rise in here other opportunities, and just keep